Hello and welcome back to Mrs. Stroder's chemistry class. We're going to talk about section 3 of chapter 10 with changes in enthalpy. Our objectives today are using Hess's law and standard enthalpies of formation to calculate delta H. Actually, today we're going to focus on Hess's law. We'll do our standard enthalpies will actually be tomorrow. So Hess's law states that the overall enthalpy change in a reaction is equal to the sum of the enthalpy changes for the individual steps of the process. If you remember, enthalpy is the total internal energy. So the total internal energy of this process is equal to, of this reaction, is equal to the changes, the sum of those changes. Sum means we're going to add. Okay, so if we know all the steps of this reaction, we can add those up and get to a overall reaction, or overall enthalpy. If two processes start and end at the same place, same reactant, same products, they have the same enthalpy change even if the steps are different. It doesn't matter what the steps are to get there. As long as they end at the same place, they'll have the same enthalpy. So Hess's law says I'm going to use my chemical equations. I'm going to manipulate them using rules of algebra. Hopefully you remember your rules of algebra. If you change sides, you subtract from both sides. You can multiply anything you want by a number, as long as you multiply everything by that number. We're going to use those algebra rules. So if I add or subtract an equation, I'm going to add or subtract the delta H. If I need 2 of something or 3 of something on one side and I multiply, I'm going to have to multiply delta H. Whatever you do to the equation, you also do to delta H. If you multiply, you do it to delta H. I can flip the reaction, essentially making the products become reactants and the reactants become products. I'm essentially changing sides. I'm subtracting the same amount, the reactants on the product side and the products on the reactant side. If I do that, I also change the sign. It becomes positive to negative or negative to positive. Change the sign of it. So the whole idea is I want to get to the point of knowing a final process or a final reaction without having to actually do that reaction to figure it out. Sometimes I do it because reactions are hard to figure out. Sometimes I do it because it's easier to look up the standard reactions that I already have done and find out what the delta H would be. So I have this reaction. Phosphorus and chlorine react to form phosphorus tetrachloride. I know this delta H. And let's say that I've done this reaction or I've looked this up. It's a standard that I know. Okay. I can also prepare it with a two-step process where I take P4 and chlorine to get phosphorus tetrachloride, and then I fit the phosphorus tetrachloride with more chlorine and I get the phosphorus pentachloride. Each of those has its own delta H for each of those. The second reaction has to take place 4 times in order for this reaction to occur correctly. So this one I had to multiply by 4. Everything got multiplied by 4. Okay? And the reason is I needed 4 in this reaction to make these, in order to make these two add up to the first reaction. I needed 4 of these. So I multiplied all sides of it. Everything goes by 4. And I get this for this is the enthalpy per kilojoule if I do it 4 times. I then add these up. This is the sum of these two, H1 and H2. I get the total enthalpy is negative 1596, which is equal to this enthalpy. So it doesn't matter where I started from, as long as I finish at the same place. It doesn't matter the steps that I go through. When I start and end at the same place, I'm going to have the same enthalpy change. So you're going to have problems like the one you see here. Find the enthalpy of formation of carbon monoxide when solid carbon and carbon dioxide gas are the reactants. Now, there's a couple of reactions that are known. Reaction 1 says that if I take carbon and oxygen, I can make CO, carbon monoxide. If I take the second reaction, carbon plus oxygen, I can make carbon dioxide. So if you're looking at this carefully, you can see the problem I have here is that these two, either one of those could be made. And how do I stop this carbon from reacting with this? So in a reality, it's really, really difficult to measure. This is difficult to measure. But I need to find out what it might be. So what I would do is figure out the sum. As long as it doesn't matter how I get from the starting point to the ending point, as long as I get to the correct ending point, it's going to be the same delta H. So I don't actually have to do that reaction. First, I'm going to look for the products and reactants of the desired equation in the given and known equations. So I'm going to look and say, where are all of these located? My carbon is here and here. Okay? I need to make sure my carbon reaction works out to be the right equation. Okay, works out in the right place. Carbon is also right here. So carbon's actually in 3 places, which is kind of difficult to start looking for. I look for something else. My CO2 is only in 1 place, right there. Okay, that's actually where I want it to be. The carbon monoxide, the CO, is right here. Okay, it's on the correct side of the equation. And I've also have this extra stuff right here. I don't want this. So I need to figure out, number 1, how to get rid of the oxygen, and number 2, how to get the carbon dioxide to the correct side, how to get rid of these to the correct thing. So what I'm going to do is, again, plan your work, look for it. Let's take a good visualization of where things are at. The first equation, number 1, I'm going to leave as is because it's got my carbon dioxide where I want it. So I'm going to leave reaction number 1 as 2 carbon plus oxygen goes to 2 CO. And it's got the right number in front of it too. So that delta H equals -221 kilojoules for that reaction. Reaction number 2 now. It's got the right thing, the carbon dioxide, but not in the right place. This is on the product side. It needs to be on the reactant side. So I want to flip this one. So flip the whole thing. So the product, CO2, goes to the reactant side. And the reactants, carbon plus O2, go to the product side. Now what that means is for my delta H, I'm going to change the sign. Positive 393 kilojoules. Now I'm going to make sure I add these up just to make sure I did things right. So my 2 carbon comes down here, plus oxygen, plus CO2. So everything on this side goes down here. Okay, on my product side, all of this is going to go here. 2CO plus carbon plus O2. Okay, now this reaction doesn't look like the desired reaction yet. Okay, well, what can I start canceling out? If I start thinking anything that's the same, I can cancel out. Oxygen is on both sides. Same coefficient. It's going to cancel out completely. Everything else looks like it's where it needs to be. Oh, and nope, my carbon on that side, there's 1 carbon. This 2 minus that carbon gives me 1 carbon, which is what I need. Okay, so this now looks like what I need my reaction to look like. So I'm going to take my delta H's and add up -221 plus 393 kilojoules, and I get 172 kilojoules. That's the delta H, or the enthalpy change for this reaction. there's some tips and tricks. Please write these down in your notebook. You're going to need to be able to do these on your own. So pause the video if you need to when I finish talking about this slide and write them all down. When you're looking at it first, pick the product or reactant that's only in one place. If I started the other one trying to balance my carbon that's in two places, I'm going to have a very difficult time trying to balance it, because how do I make two of them into one? The next tip or trick here, is to multiply, divide, or flip the equation with a known delta H to match the coefficient in the unknown. So if I had a 2, I need to multiply by 2. If I have 3, I'm going to multiply by 3. Okay. If I need to flip it, I change the sign. Next thing, add up all the equations and then make sure. Make sure means do this step down here. Cross things out. Make sure that you're really right, that you really have the right thing. Does it really cancel out completely? You might find the lowest common denominator sometime. You may have to add or subtract fractions. I know you guys do not like fractions. Sometimes you have to use them here. And, you know, if it's plus 1/2, minus 1/2, a third, you may be doing some things with fractions. 1/3 and 1/2. Make them into common denominators. 2/6, 3/6, if you have to add and subtract fractions. So we're going to do another trial here. One more practice problem for you. This one's tricky because it doesn't actually give you what the reactions you're trying to find. So first thing you have to do is say methane and oxygen. So CH4 plus O2. Usually you'll be given the reactions. I won't usually do this to you. React to form CH2CO and water. Before you can actually balance this, you need to figure out, or before you can actually do Hess's law, you have to have it balanced. I know I have to increase my carbon. Oxygen, I have to balance my hydrogen out first. I have 8 here, so I'm going to put a 3 right here, which gives me 8 hydrogen on that side. So I'm going to balance my oxygen with a 2.